Welcome to Calculus, Semester 2. Today we are diving into the fascinating world of curve tracing. Imagine you are tasked with drawing a highly detailed map of an entire country. You wouldn't measure every pebble. Instead, you would look for major landmarks like mountain peaks and coastlines. Curve tracing works exactly the same way for mathematical equations. We will learn how to find the mathematical landmarks of an equation, allowing us to draw a highly accurate sketch of its overall shape with minimal effort. Now that we understand what curve tracing is conceptually, let us look at how it works in practice. Curve tracing is essentially an analytical method of determining the rough shape and behavior of a mathematical curve using tools from algebra and calculus. Why does this matter? Because blindly calculating and plotting hundreds of individual points is incredibly inefficient. Instead, it is a detective process. We use specific math rules to find the skeleton of a graph. We look for several specific features to build this skeleton: symmetry, intercepts, asymptotes, and extrema. By finding these key landmarks, we can sketch the true shape of the curve effortlessly. Before we look at the exact equations, let us understand our first major landmark: symmetry. Why do we care about symmetry? Because it tells us if the graph acts like a mirror image of itself, which literally saves us half the work. If we know the right side of the graph, symmetry allows us to just copy it over to the left. The first type is y-axis symmetry. This means the curve is perfectly balanced across the vertical center line, like a U-shaped parabola. Now that we know what symmetry is, let us look at the mathematical test for y-axis symmetry. This formula comes from the idea of a perfect mirror reflection across the vertical axis. In this equation, f of x represents the original function, which gives us the vertical height at a positive horizontal position. The term f of negative x represents what happens when we replace every positive horizontal position with a negative one. If plugging in a negative number gives you the exact same height as the positive number, the equation holds true. Physically, this means if you walk 5 steps to the right or 5 steps to the left, you are standing at the exact same elevation on the curve. While y-axis symmetry is useful, there is another type we must look for, called origin symmetry. Conceptually, this is a slightly different mirror effect. Here, whatever the graph does in the top right corner, it does the exact opposite in the bottom left corner. If the curve goes up and to the right, it must go down and to the left by the exact same amount. This type of symmetry is common in odd functions, like a wave that passes perfectly through the center of the graph. This brings us to our second formula, which is the test for origin symmetry. Conceptually, this is a slightly different type of mirror effect common in odd functions, like a wave passing perfectly through the center. Here, when we input a negative horizontal position, the resulting height is the exact opposite or negative of the original height. Let us break down the symbols. The left side, f of negative x, is the height on the left side of the graph. The right side, negative f of x, means we take the original height and flip it upside down. If these two match, it means if the curve goes up and to the right, it must go down and to the left by the exact same amount. Having covered symmetry, we must now look at our next set of landmarks, asymptotes and extrema. Why are these important? Because they define the extreme limits of our map. Asymptotes are invisible boundary lines that the curve gets infinitely close to but never actually touches. They tell us the long-term behavior of the curve as it travels infinitely far away. Extrema, on the other hand, are the absolute highest peaks and lowest valleys on the graph. To find these peaks and valleys, we use the first derivative from calculus, which tells us exactly where the slope of the hill is perfectly flat. This formula represents the mathematical search for a horizontal asymptote, our invisible boundary line. Conceptually, it asks a simple question: what happens to the curve as it travels infinitely far to the right or left? The limit stands for exactly that. The symbol X represents the horizontal position, the arrow means approaches, and the infinity symbol means we are looking at the far edges of the graph. If the curve flattens out and approaches a specific constant height, represented by L, then we draw a dashed horizontal line at that height. As x increases forever, the physical distance between the curve and this dashed line shrinks down to zero, meaning the curve will hug this line forever. Before we move on, let us see this with a concrete example. We are given a rational function, where one polynomial is divided by another, and we are asked to sketch its entire shape. Our strategy is to test it step by step. First, we check if it has any mirror-like symmetry to save us time. We replace every x with a negative x. Because squaring a negative number turns it positive, the bottom of the fraction stays exactly the same. However, the top becomes negative, making the entire result the exact negative of our original equation. This proves the curve has origin symmetry, meaning the bottom left will be an upside-down mirror image of the top right. Continuing with our detective work, we next need to find the exact locations where the curve crosses our main axes. These crossing points are known as intercepts. To find the y-intercept, we simply set the horizontal position x to 0 and calculate the resulting height. The math shows that when x is 0, y is also 0, placing our curve right dead center at the origin. Next, we investigate the extreme edges by checking for asymptotes. We look at the limit as x grows infinitely large. Because the bottom has an x squared, it grows much faster than the single x on top. When the bottom gets massively larger, the overall fraction shrinks to 0, meaning the curve flattens out along the horizontal axis. Now that we have our intercepts and boundaries, we must find the peaks and valleys of our landscape. To do this, we calculate the first derivative, which represents the steepness of the curve at any given point. Because our original equation is a fraction, we use the quotient rule from calculus. We multiply the bottom by the derivative of the top, subtract the top times the derivative of the bottom, and divide it all by the bottom squared. By multiplying the pieces out and subtracting them, we simplify this messy equation into a much cleaner expression. This simplified formula is our slope finder for the entire curve. To find exactly where the hill is perfectly flat, we set the numerator of our derivative to 0. A fraction is only 0 when its top part is 0. A slope of 0 means the curve has stopped going up and is about to go down, or vice versa. Solving this simple algebraic equation gives us two critical points, positive 1 and negative 1. If we plug positive 1 back into our original equation, we get a height of 1/2, which is our highest peak. Plugging in negative 1 gives a height of negative 1/2, our lowest valley. We now have all the landmarks we need to draw the map. Let us look at the final result of our detective work. Here is the complete graph of our rational function. Notice how every landmark we calculated is perfectly visible. Right in the center, the curve passes through the origin at 0, 0, just as our intercept test predicted. Moving to the right, it climbs to a smooth peak exactly at the coordinates 1, 0.5. After this peak, watch how the blue line slowly flattens out, hugging the horizontal x-axis forever without crossing it, which is our horizontal asymptote at 0. Finally, because of origin symmetry, the left side does the exact opposite, dipping into a valley at -1, -0.5 before fading away. Now that we have successfully traced a curve that stretches to infinity, we must consider a different scenario. Sometimes mathematical equations have built-in restrictions, meaning the curve simply does not exist in certain areas of the graph. We call these restricted areas the domain of the function. Why is this important? By finding these boundaries first, we can draw an invisible box on our paper and know for a fact that our curve will never step outside of it. This saves us from wasting time looking for landmarks in places where the curve cannot possibly go. This brings us to a new type of equation, one that forms a complex loop. Let us examine the formula. Notice that the vertical variable y is squared on the left side. Conceptually, this immediately tells us two things. First, the graph will have top to bottom symmetry. Second, because any real number squared must be positive or zero, the entire right side of the equation must also be positive or zero. If the right side ever becomes negative, we would be trying to find a number that squares to a negative, which is impossible in standard graphing. Therefore, this specific formula has a strict rule built into it about where the horizontal position x is allowed to exist. Let us apply our domain concept to this example. We need to find the exact boundaries where this curve is allowed to exist. To enforce our strict rule, we look at the pieces on the right side of the equation. The x squared part is always positive, so it never causes a problem. However, the part inside the parentheses can easily become negative, depending on what number we plug in. Because the overall right side must be positive, the part inside the parentheses must be greater than or equal to 0. Solving this simple inequality tells us that the horizontal position x must be less than or equal to 1. The curve completely stops at this vertical line. Continuing with our loop curve, we now find where it crosses the horizontal axis by setting the vertical height y to 0. This leaves us with the right side of the equation set equal to 0. In algebra, when two things multiply together to make 0, at least one of those things must be 0 itself. This gives us two separate easy equations to solve, resulting in x equals 0 and x equals 1. These are our two x-intercepts. Because the curve exists between these 2 points and has top-to-bottom symmetry due to the y squared, it actually forms a closed loop between 0 and 1, splitting into branches to the left of 0. Now that we have traced both infinite curves and closed loops, you might wonder why this matters in the real world. Curve tracing is the absolute foundation of understanding how physical systems behave over time. Engineers use these exact analytical techniques to predict the trajectory of a rocket, ensuring it reaches orbit instead of crashing back to Earth. Economists use the first derivative to find the peaks and valleys of profit models, helping businesses maximize their efficiency. Without the ability to trace curves analytically, we would be blindly trusting computers, and we might miss crucial, dangerous behaviors like a sudden spike to infinity in an electrical circuit. We have covered a lot of ground today, so let us summarize our key takeaways. Curve tracing is all about working smart, not hard. By treating a mathematical equation like a puzzle, we can extract key pieces of information to build a solid framework. We use symmetry to save time, intercepts to anchor the graph, asymptotes to find the boundaries, and derivatives to locate the extreme peaks and valleys. Once this framework is in place, sketching the actual curve becomes a simple matter of connecting the landmarks. You now have the tools to truly understand the why and how of a function's behavior. Great job today.